Okay, thank you very much. My name is Elma-Maria Charlampidou. I'm a civil engineer and assistant professor at Heriot University. Really excited to be here with you today to present you some work on water flow within deformed and undeformed samples from Glasgow observatory. A little bit about the motivation of this work. So this work falls within a broader scientific interest theme that relates to better understand the behavior of non-homogeneous materials and systems. The UK Glasgow Geoenergy available core is an ideal material for that purpose. Moreover, it relates to turning mine water geothermal energy into a viable alternative source of sustainable energy, which is really exciting. Therefore, we are very much interested in understanding the hydrothermal-mechanical behavior of these systems. And today I'm going to focus only on the hydromechanical decoupled behavior. And some of the samples I'm going to show you, they have been previously squeezed triaxially at the laboratory scale. So the material that we are using in this work comes from the GGC01 seismic observation borehole. And Dave has shown some results from this borehole previously. There was a number of samples that were collected coming from different depths, and today I'm focusing on 3 of these samples, which are mainly consisting of sandstones. The results I'm discussing are the outcome of a combination of 2 experimental methods, X-ray and neutron tomography. Both methods are non-destructive and they interact in a different way with the matter. So when it comes to X-rays, then the photons interact mainly with the atom's electron cloud, whereas with the neutrons interact with the nuclei of the element. Therefore, the sensitivity of the methods also is somehow different. If we consider that the photon energy and the atomic number of the material that we are studying are kept constant, then basically the X-ray tomography maps density variations as opposed to neutron tomography when neutrons are sensitive to different isotopes, for example, hydrogen and deuterium. And in particular, when we have flow experiments where both water and heavy water are present, then the hydrogen in the water has higher attenuation coefficient with neutrons as opposed to the deuterium, which is more transparent. But when both of them exist in the same system, then the contrast between them is really good, and we can observe the flow migration within the samples of interest. The samples that we have taken for the borehole, some of them were squeezed under triaxial compression at the Heriot University Rock Mechanics Lab. They were scanned with X-ray scanner before and after any operation, and some of them were taken to HZB neutron beamline, where flow experiments were performed by performing also 1-minute time-lapse neutron tomography. The sample was sitting on an aluminum cup, as you see here, and the flow injection was taking place at the bottom of the sample. Any water that was migrating through the samples was concentrated at the top reservoir. At the bottom of the sample where the injection was taking place, we have also installed some pressure transducers. Therefore, we were able to capture the evolution of the inlet pressure in the sample. And here you can see the example of the inlet pressure within 4 samples that we have scanned at HZB. During the flow tests, and we see that this pressure evolution changes within the 4 different samples. And in the following slides, I'm just going to comment why this has taken place. Sample 66 is a sample with natural fractures, as we can see from an X-ray static computer tomography. So the fractures are inclined, some of them are vertical as well, and they have a very complex trajectory sometimes. The top part of the sample consists of lower density material, and the rest of the sample is relatively high density. When we compare this image, this cross-section with that coming from a neutron static commuter topography after the post-flow test, then we see that these fractures are mainly covered by bright colors, which are indicative of water, so they're saturated with water, and also some layers that interact with these fractures start getting brighter colors, and the top part of the sample, which was a lower density material, also gets fully saturated. When we observe the time-lapse tomography throughout the flow experiment, and here I'm showing the inverted time-lapse neutron tomographies, we can follow the process of water migration throughout the sample. So at the very beginning, we see only some darker regions which are indicative of potentially organic, which are zones potentially rich in organic matter, so they contain some hydrogen. As the water migrates, it goes through these zones, and these zones get brighter. In the inverter maps, they get darker. And the migration then follows some fractures, some vertical fractures, as you see here. The water migrates to the topper part of these zones until the moment that it reaches the top reservoir at the end of the experiment. After about 150 minutes of the start of the experiment, then we had a kind of uplifting of the sample because of the pressure that has been created at the bottom of the sample. And I'll try to illustrate the whole process with this video here, where we see that the water gets into the sample, the zones get darker, so they get saturated, the water migrates through the fractures and reaches the top part of the sample. So we have an interaction between these zones and the vertical fractures. Sample 54 is somehow different. So this has a low porosity material at the bottom and higher porosity at the top. And we observe some horizontal or semi-horizontal low density zones, very thin zones. Here you can see the cross sections of these zones. These are possibly some coal seams or some fractures which have been sealed. During the actual experiment, the flow migration follows somehow different patterns. So the water saturates the bottom part, and as it propagates, it leaves unaffected the region in the middle of the sample. As the pressure builds up, the full saturation of the sample takes place. And we can see here as well the migration throughout the sample. In this particular part, the horizontal fracture or coal seam that was identified by lower density material seems to not play any substantial role in the propagation of the water within the system that we study. Sample 135 is a sample that has been squeezed in the lab at 20 MPa confining pressure. And here I'm comparing two vertical cross sections with X-rays before and after the deformation. So we can see the presence of some organic material here, lower density, and we see in this slide the creation of the lab-induced fractures. Some of them cross-sect the organic matter. The post-failure flow tests give us some further information about the saturation of the sample. For example, the main big fracture that has been created appears to be brighter, so it's water saturated, whereas the smaller fracture that intersected the organic matter seems not to be affected. This could possibly be because the tip of this fracture is in a region which is characterized by higher density material, so the water couldn't get into that fracture. Following the flow experiments and the time-lapse tomography, here we see that the initial fracture in a different cross-section here is initially non-saturated, and as the water migrates into the sample, it propagates through the fracture, and at the same time, it saturates the zones that have some organic matter, so they are darker, you see from the very beginning, and then there's an interaction throughout the test between the front propagation, the water propagation through the fracture, and the saturation of these inclined zones. And this video illustrates better this process. So going to the discussion, which also stands for the conclusion section, I would try to wrap up the take-home messages. The lab-induced fractures greatly facilitated the waterfront displacement, particularly in these low-perm materials. There was always an interaction between some more permeable zones, which could be channels, layers, or zones with organic matter, and the pre-existing fractures, either natural or lab-induced. The different depositional phases that we have seen within the samples and the layers did alter the hydraulic behavior of the material. In these three cases, the waterfront has migrated in different ways, although in two samples where we had the fracture presence, there was an interaction and interplay between saturation of the fractures and the layers that the fracture were connected to. And neutron tomography in combination with other methods, for example, here X-ray tomography can help us to get better and deeper understanding of the subsurface roles. They provide 3D and 4D information during the actual operation that we perform in the lab, and they can give us information about the flow pattern, migration, and the behavior of the system. These samples were relatively big, 38 millimeters in diameter, and by combining neutrons and X-rays, we were able basically to capture all these processes. So thank you very much for your attention, and I'm happy to answer any questions that you might have.